Okay, so let's continue, please. In the last session, we were computing the cutoff energy. Please remember this. We arrived to this picture. So when I ask, okay, a few things before we continue with this is that this is the energy. Look, this is the total energy of existence per atom, not total energy. You see. And this is the cutoff energy. I remind you the cutoff energy is related with the number of plane waves I use to describe the constant wave functions. This we're going to see during in theory, what in during the theory sessions from where it comes from, what we will do without and why it is. But this is related to this. The bigger the cutoff energy, the better, or the more plane waves we use. It is really, it is similar to the Fourier transform, right? To describe perfectly any kind of function, you have to use an infinite series, right? But you can use some approximation to get some accuracy, right? What is my precision here is 1 millielectron volt per atom. That is my criteria of convergence. As you can see here, if I go higher and higher, we are in this plateau, basically, right? But it looks like a plateau, but it's better to do the zoom in this region. So basically what I do is I choose the lowest value here. In this case, that is not generative. I take the lowest value of these points. For this case happens to be this. In most cases, many cases could be some point here. At that point, I make a window of 1 millecron. So what I'm doing here is I'm doing a zoom, as you can see here. I do a zoom of the late. This is the last value. Why the last value? Because in my case, the last value was the lowest one. If you check here, you can check it. How do you know this? Because you can check here, right? You see, what is the lowest value? It happens to be this here. You see, 85. You see? In this case. So the first thing is you have to check in this table which is the lowest value. For what value of the cutoff energy is the lowest value. Okay. And from that value, you said I'm going to make a window of load range from this to up 1 millecron volt per atom. So that's the reason why here these values were obtained. What I did here, as you see, I did import that data we compute, and after we apply a transformation where I divide the second value, so the energy is by 2. So this 2 is because it is the number of atoms. So this here is the number of atoms. How many atoms has the system? 2. How do I know? Check the postgraph file, check the outgraph file, which is going to tell you how many atoms we have. So, okay, so we have this, and we plotted this, right? We plotted this. So this is the window. So what is the value we should take to do the calculations? One. So as I mentioned here again, here's the result. I just plot the whole data, and I need to find the convergence, right? The convergence means that from which value, in this case, the cost of energy, I have already convergency of 1 millecron per atom, right? So in this case, if I do a plot, on this, you see in this window has to be all the points, not maximum points, right? So here was, in this case, the lowest value was here, right? That's the reason I put this window from here to here is from here, from this value here, all this up to here is 1 millecron per atom. So all these points inside of this window has already a convergence of 1 millecron. So which value shall we use for the cutoff energy? 100, 900? Yeah, why we use 400 but not 900? What's the reason? Because we know since all the points are inside this window, we know that all these cutoff energy already converts to the energy to 1 millecron per atom, right? That's it. Of course, you can use this 900. The results are going to be exactly the same as, or almost the same as 400. In fact, it's going to be the same within that criteria of convergence, right? Let's suppose there was other point here. So I should use that one, right? Sometimes happens this, by the way. So sometimes, unfortunately, I cannot write this. Okay. sometimes happens this, this. You have this. That's the thing I was telling you. Sometimes, in many cases, that is in fact that's the most normal. You have this. You calculate the points, and suddenly you see this. See, look. Sometimes you can find this when you learn the points. Let's suppose when the point is on this. So the question is, what is the converse from which point from which value we have convergency? In that case, you have to make a window from where to where? From this value, right? Plus 1 mV. So let's suppose I do this and this. See, all this window. You see? Let's suppose that is the window. Can you see? So which value should be in this case, let's suppose that this red dot here is just outside of it. Here. In this case, from which value we have a convergence of 1 mV/hour? This point? Anthony, this point? This point is inside of the window. Angel, you see, that is the window of 1 mV/atom. I am asking you from which value we have a convergency of 1 mV/atom. What do you think? Okay. Body, nuclear. Steven, it's something that you are going to face right away in your midterm. And midterm project exam. You have to decide what is the. So which value should be the in this case? Because this here was very easy, right? But here, this one, maybe this one, maybe this one. Diary.
Point
Hmm?
outside the,
But say again,
from the next point outside the next.
this one. So Diane says this. Could I?
This one.
Steven?
I think it could be arranged.
Arrange? This is the range.
Oh, okay.
So you have to choose. This is the criteria 1 mV/atom. Remember, this point here is outside of this. This point is outside. Anthony? Wanda? Ángel? Anthony? Santiago?
I think the next point on the one that leads just to us.
Okay. Attention, please. Full attention, everyone. So the correct answer is that, right? Is from this point and above is this. But you will say, wait a minute, but you told me all since I see the first point inside of the energy window, has to convert the energy 1 mV. You say this one. But what is the problem? It's this point. Because of this point, this does not qualify as a criteria of 1 mV/atom. So remember, it has to fulfill all the points mean all the points and above. Let's suppose that if we consider this continuously, we can get all the other points inside of the cells. I'm not going outside of this. There is a window for this. See, therefore this is the not this. Why not? Because if I go up, I go a point that is outside of the convergence criteria, it means that this is not well converged. This also, because if this does not converge, all these are not outside. Okay? Is that clear, please? Somebody want to repeat? It is recorded, unfortunately, it's not recorded the screen, but at least it's the audio. So you really remember this. Okay? So remember this, in this case, it was very simple because, all the points, above, from starting from this point, all the points are exactly inside of this range. So that's the reason we can pick up this. In the other case, you have to be careful. That's the reason you have to visualize. I know there are some people. In fact, I have met some people just by looking at the data, they can tell you this. I cannot do this. They have to visualize. But there are some people or some students that are this kind of abstraction to visualize data. And just by looking to the table, I don't know how they do it, but they just by looking to the table, they will infer what happened. Okay? I know I am not good visualizing data and assessing. I have to. So please do not, if you are very confident and you have this ability, okay, that's it. So just by looking to the table, you can say, yes, it is for this value here, you see, 0.1. But sometimes I've been doing this and sometimes I fail. So from now, so that's in my case, yeah, that's it. I have to visualize the data, and from that I can work in the comments. Okay. Is that clear, please? Anyone? Okay. So we went to this. Now, what we are going to do is we're going to find the convergence on the K points, right? Why the convergence on the K points is related with the reciprocal space. As I mentioned, all these calculations we do in reciprocal space is a consequence of using periodic boundary conditions, because we have to use block functions, something that we're going to see next week in the theory. And because of that, we use the reciprocal space. And in that space, in the reciprocal space, we define the first Brillouin zone. And inside of the first Brillouin zone, we should compute an infinite number of points. But there is a theory, the many theories, one of the most used nowadays is the Monfort fact. He provided that you can approximate the integral of a periodic function with a sum of the same function in certain points. These special points we call the Monfort fact grid. And this is this, the K points is the grid 4 by 4, 4 by 4, 4, 5 by 5, etc. So we're going to do this, please. So to do this, go to you see, we go to this folder, and we are going to run this. Please open this K points stage, and we have this. You see, in my case, only my case, and also in Edward, but Edward missed this lecture. Edward, you have to do this. If you see this recording, you have to please put. In your case, I should put Edward, as I mentioned yesterday, put 4. In your case, you can put 4. Okay. I'm going to put 2 because somebody asked me again why you use 2 is because I don't want to fly, because I want everyone to get this. Okay, so there it is. That is my K points, the script to do the K points. See, if you want to have the best details, my recommendation is copy the whole script, put it in DeepSeek, and ask to DeepSeek what exactly it's doing. Just as a summary, here we're going to create a grid for K going from 3 to 12 in steps of 1. What K points, because remember you need a K point 5. So the K point 5 is going to create this, depending on this, you are going to create, first when you start with 3, will be here like this, and 3, 3, 3. Next will be 4, 4, 4, 5, 5, so. And after that, it's going to subtract the total energy, remember, without entropy, with sigma 0, from the outcome 5, and it's going to create a list of the K and this energy. I'm going to put the K point. That's it. So let's run it, please. So let's do this, please. Before you run, don't forget to do this, please. Remove. In some computers it will work, but in general, please try to do this, okay? Pass this. So I recommend always to start doing this. Okay, just It's just to make it to skip any kind of error we find. And now I'm going to run this, no? Like this. We're going to run the cap points. That's it. It's running. Don't worry to me. This warning message is because of the compilation in my architecture in Mac, but some of you don't have this one. Okay. We're completing this, and mine is finished. Okay. So the result is written in the file called kps.dat. So I'm going to open the file kps.dat. There it is. And I leave it here, okay? So I will put it here, and I will pause this. Okay. Okay, I have to repeat it. I'm going to repeat this again, please. What I did is I'm going to remove this kp that this I'm going to look this here. If you want to edit this, please, I don't put any space here. In your case, I don't recommend to do this. Just keep it like this, Just keep it like this, okay? Because I know that all of you can use all the course, but only in one case was the problem with or some other students, so I recommend this. Look, I don't put any space between this, otherwise it won't work. First thing. Second thing is, sorry, it was my mistake. In the Inca file, you have to change this to 400. That was my mistake. Okay? To change this to 400. Why because 400? Because the cutoff energy, in our case was 400. The convergence of the criteria was 400. That I forget this, Of course, with that 100, you're going to find almost no error, almost no difference, but please use 400 because the bigger the cutoff energy, the longer will take the cutoff. Please, I did this in the file. It is recorded, please. And now you're ready to go. Okay. So I'm going to save it this. Just double check, please. I'm going to say this. Double check the Inca file that you have this. You see, 400. And it's written, by the way, in the manual, just in case, In the manual says, here this. Look, however, remind to put line and cut equal to 400. Please remember, always follow instructions. If you don't follow instructions, something else will happen. Now let's go. We are going to run again. Okay, so I'm going to run again. Remember, there is no way, so I'm going to remove any wave path, whatever, okay, to run it. Okay, so I'm going to run, and that's it. So I'm going to kill this. So now it should be faster, please, much faster. Okay, I'm going to pause here. Okay, let's finish this, and after I'm going to pause my recording. Okay, so I'm going to open the cap points, the data I created, and this is the data. Okay, so you should have something similar, and I'm going to. Okay, so now I'm going to start again, repeat again here because I'm recording, please. I upload this so to set up where is my directory that I'm working, and now I'm going to do this analysis of the key points, and this will be a subsection, please. Subsection, okay? So let's do this. So that I'm going to call data KP equal to input, right? This data, this is what is called KPS date. And again, since we need energy per atom, so I have to do math. So I have to transform this to this, right? This divided by two total atoms. El- There it is. Okay. Okay, so I have this. And now, please do not, so just copy this place from the previous part. This one here, you see, the cutoff area. Paste it and edit it, right? So I have the data copy, see? Exactly the same. But now in this X level, I'm going to put like this, KPS. Okay. Points. And energy electron volt per atom is exactly the same. Interpolation is exactly the same. Okay? Unless there it is. You see? We have this. I repeat again what I did. Please, is recorded. I'm not going to repeat, just I'm going to copy this, please, from the previous section, remember, from the cutoff energy. I'm going to copy this, please. Paste it here, please. Replace this in the state that you have KP, right? And in the standard cut, you have K hyphen PTS, so K points, right? Got this. Shiventa. There it is. Okay, now I'm recording. Okay, now I have to say, as I mentioned before, just by looking the data, it's not easy to see what is the convergence in this data. Of course, I can see a plateau here, but I cannot tell exactly from which point is already converged, has the convergence. So what I do is I copy this as we did with the cutoff energy. I set here, and the plot range instead of this, I'm going to put like this. Minus 1,2, the same. Minus 1,2 plus 10 to the minus 3. Right? The same as, and there it is. See? There it is, please. So in this case, it's, right? In this case, clearly is not 8, it is 9. Okay? So I put a note here. So from this result, for this system, we use K-grid 9,001 points. And the K points 5. Okay, that's it. Okay, so don't forget to put this. Okay, it's just, so I'm just explaining some ideas how to start to complement your file. Okay, okay. Somebody asked, some student asked, why we use this grid if you see the K points, it's set up like this, You see? The K points grid, it is KKK. So all the values are the same. Is that general? No. This grid depends on the shape of my crystal structure. If the shape of the crystal structure, let's say, is rhomboedrical, that's it. These values will be different for each direction. Okay. But you might ask, how do we know? I will teach you later to compute, I'm going to teach you how to compute the reciprocal lattice parameters and how to get the grid exact. So there is a specific algorithm that is built in VAS, but we are going to do it by hand to check this, okay? So we will do this. So be careful with this. Thank you for the question. I repeat for the last time, for the second time, that this grid here, in this case, is this KKK, or the same values in all directions, because in this structure, A, B, and C are exactly the same. That's the reason why. It's an FCC, so that's right. But it might happen you are going to have other system. In another system, cannot in most of the cases not the same grid for all these values here. But how you compute this? We compute the reciprocal lattice parameters, and in those lattice parameters, in that we try to find for a specific delta K in each direction, how many times is divided, and that value will give us this value. Okay, so. More questions here, please, somebody? Somebody, please? No? Okay, I'm going to pause this here.